We've talked about the fact that sound travels as a wave. And we've also seen previously in this unit that any wave that we can talk about has a specific velocity, a speed, and a direction. And so we can talk about the speed that a sound wave would have. And as we'll see and talk about more in class, the speed of sound could actually change depending on what material the sound wave is traveling through. For these first few calculations that we'll do in the video here, though, we're going to focus on the speed of sound through air. And what's been found is that through air, when we're dealing with the typical amount of air pressure that we have here near the surface of the Earth, and we're at 0 degrees Celsius, we can measure that the speed of sound is about 332 meters per second. But what we've also noticed is that that speed seems to change when the air temperature changes. When the air temperature increases, or it gets hotter outside essentially, the air particles move a little bit faster. And that allows them to transfer their energy from one to the other a little bit easier, and allows the sound wave to actually move faster. So an increased temperature leads to an increased speed of sound. And through some careful measurements, what they've realized is that every time the speed of sound, every time the temperature goes up by 1 degree Celsius, the speed of sound increases by 0.59 meters per second. And that leads us to a nice little equation, because it says that we could start with 332 meters per second, and then every time the temperature goes up by 1 degree, we'll add 0.59. Every time the temperature goes down by 1 degree, we'll add negative 0.59. Or in other words, it's like we're subtracting 0.59 every time the temperature changes by 1 degree. And so that's where this other part of the equation comes from, that we're going to add 0.59 multiplied by whatever the temperature is. And what's nice is for that value T, for temperature that we're going to sub in, it doesn't matter if it's a positive number or a negative number. And now we can use that formula and see what kinds of things we can learn from it. So for example, if we have a man who's shooting a gun at some clay pigeons, so just doing a little bit of target practice, and we know that it's 20 degrees Celsius outside, we should be able to figure out how fast the sound is traveling away from his gun. If we just list some things that we know, we're told again that temperature is just 20 degrees Celsius. And we also know in this case that speed of sound is 332 meters per second at 0 degrees Celsius. But we don't actually have to write that in our givens. And so in this case, we actually don't really have any other given information we need to write. But it's velocity that we're going to try and find. So our formula, once again, is 332 plus 0.59 multiplied by temperature, T. So that's 332, and in our case, it's 0.59 multiplied by 20. When we multiply those numbers and then add them with 332, we get 343.8, or approximately to 2 sig digs, I could say it's about 340 meters per second. And so again, if the temperature of the air was just 0 degrees, we know the sound wave would be traveling at 332. But because it's a hotter day than that, that hotter air allows the wave's energy to be transferred from one particle to the other a little bit quicker. And so the actual wave itself travels a little bit quicker, and in this case, a little over 340 meters per second. What's great about this, though, is that we can also use this to solve other kinematics-related questions. What we need to keep in mind, though, is that the speed of sound, as long as it's only going through one kind of medium, essentially one kind of air or one kind of water, that speed of sound stays constant. And so as long as we have kinematics formulas that can deal with constant velocities, we can solve other things related to that. So in part B, we're saying that if it was to take 5 seconds for the sound to travel from the gun to our ears, we can figure out how far away the actual gun is. So in this case, we know velocity because we just found it. And I'm going to use the unrounded version, 343.8 meters per second. And we are also given that time is 5.0 seconds, and we're just looking for displacement. We're looking for d. Well, because it's a constant velocity, we just use the simple kinematics formula that says that velocity is equal to displacement over time. But the way we want to use it is to say that displacement is really velocity multiplied by time. So in our specific case, that's taking 343.8 and multiplying by 5.0 seconds. When we do that, you'll get 1,719, or approximately 1,700 meters, or about 1.7 kilometers. And you'd want to still state a therefore statement that says, therefore, the distance that the sound would travel in those 5 seconds is 1,700 meters. Or in other words, the man who shot the gun must be about 1,700 meters away. And we figured that out just using what we know about the temperature and how it relates to the speed of sound. We should also keep in mind that that formula could be easily rearranged if we already knew the speed of sound and could measure that in some other way, and we were trying to use that to find the air temperature. So in that case, if we want t all by itself, we could rearrange and say that it's the speed of sound subtract 332 and then just divide by 0.59, and that could give you the temperature. Now the second part of the note talks a lot about what happens when we're dealing with sound waves through different kinds of materials, things that aren't air. And we'll talk about that more in class and talk about why certain materials transfer sound waves faster than others. We'll also talk about the part on the very bottom of the other side of the note, where we talk about situations where things might travel faster than the speed of sound, and we have a special way of writing and discussing those kinds of situations.